Hi guys, and welcome to this part of astronomy. We are now moving on from the solar system. We're exploring now, actually, we're still in a sense in the solar system, but we're exploring the stars. We're going to start with the sun. As you guys have noticed, whenever we try to explore any objects in astronomy, we start with what we know best. For the case of stars, the best star that we can basically investigate and study at this point is actually the sun. And so this is our starting point. So you have units 51, 52, 53, and to some extent even unit 54. They're dealing basically with the stars, but taking as an example of the sun. The sun turned out to be a middle star in a sense of its size, whether it's mass or radius, or also in its lifetime, and a lot of properties in its luminosity and things of this nature. Obviously, there are stars that are much, much bigger than the sun, and there are stars that are a lot less in terms of size and all of these properties than the sun. As we move down the road, we will be expressing units, for example, for the luminance of a star, or for its radius, or for its mass, in terms of those of the sun. So this is basically what is coming next after this few units. For the sun, of course, when you look at it with filters, hopefully, you will notice the outermost layer, which is the photosphere, basically what we see, okay? And that is the outer structure. If you zoom on it, you will notice that it has some sort of a bubbles that are boiling on its surface. And that's because of the fact that you actually have convections underneath that zone. And those basically so that's part of the structure of the sun. And that convection zone, or the convective zone, is actually immediately under that thin layer, which is only about 500 kilometers in terms of the upper surface of the sun. And that one has, at an average, about 5,800 Kelvin in terms of temperature. So this is the surface of the sun. If we use Stefan's law that we discovered in the previous units 21 through 24, we will see that the amount of radiation, just a reminder, Stefan's law actually gives you how much intensity of radiation is emitted per unit area, and it has to do with that constant sigma times T to the power 4, where sigma is a constant 5.67 times 10 to the negative 8, where all of the units are still supposed to be in the standard units, namely the power in this case is in watts, and the area is in square meters, and also the temperature is in Kelvin. So you take the temperature, in this case 5,800, you raise it to the power 4. In other words, 5,800 times 5,800 times 5,800 times 5,800, 4 times. And then you multiply it by that factor that is given by Stefan Boltzmann law, which is 5.67 times 10 to the negative 8. And then you will have a value for how much energy is basically being dissipated by the sun every second per unit area. Now, we know the size of the sun, and we have seen that before, and actually we're exploring it also in these units. The radius of the sun is 696,000 kilometers. Obviously, we have to convert it to meters. As I was saying before, we have to use the standard units. So that's 696 million meters. You square this number, and you multiply it by 4 pi. That is the area of a sphere. So if I have a sphere, and I'm interested in the outer area of it, that's 4 pi r squared. That is from simple geometry. The area of a circle, though, is only pi r squared. So we multiply by the sphere. Now we have how much radiation is coming out of the sun every second. In other words, the amount of energy that the sun dissipates per second, which is watts, which is the power, okay? So it turns out to be about 4 times 10 to the power 26 watts. In other words, joules per second. That's how much energy the sun dissipates per second. That's what gives it that brightness. That's what really gives it that energy that is coming to us. Underneath the convective zone, there is actually a radiative zone. A radiation basically is coming, zooming out of the sun, going through, warming the convection zone, and that is gases basically, mainly hydrogen and helium, that are going in a circular fashion. The lower ones are actually hotter than the ones in the upper layers of the sun. So that's a way for the sun to get rid of its energy, its internal energy, by having the hotter one rise, and as it cools down, the one that is cool falls down, and that's how basically the heat is being transferred to the upper layer, which is, as I was saying, sits at about 5,800 Kelvin. Now, below the radiative zone is where the core is. That's where the nuclear energy is. If you look at the density of the sun is about 1.4 kilograms per liter, or 1.4 grams per cubic centimeter. So it's a gas, and that's exactly similar to what the density of Jupiter is. So it's a gas mainly of hydrogen and helium. And we have other indications for why that is so, actually using spectroscopy, topic that we learned in the units 21 through 24. And again, if you look at the temperature rises and the density changes with it and increases until it becomes very high in the core. And with the temperature going up to 15 million Kelvin in the core of the sun, and also the density extremely high, now this is basically the conditions for nuclear reactions. So inside the core of the sun, you have fusion of lighter elements, namely hydrogen, and being converted into helium in the proton-proton chain. Okay. One of the questions, because the sun is so massive, why wouldn't the force of gravity collapse the sun on itself? Well, it does. Because if it were not for the force of gravity, the sun would have exploded into all the different directions and would basically have lost all of its components because of the internal pressure. So there is the nuclear reactions trying to expel materials outward. And in the same time, gravity is pulling on these materials. And as it does, the density increases and the pressure increases, the temperature increases, and that pressure, since it increases, it basically fights off that further compressions due to the force of gravity. So there is a balance in this case. If the temperature inside increases, the sun swells a little, and as it does, in this case, the temperature is released. And as if the temperature is going down, in this case, it's going to be compressed. But then as it compresses, due to changes of the force of gravity or the gravitational potential energy into kinetic energy, the temperature will increase. So there is a thermostat, there is a regulator that keeps the star at its own size, as long as nuclear reactions are still an ongoing thing inside the core. Now, if the sun runs out of fuel, namely hydrogen, at that point, there is no counterpart to the force of gravity, and the sun will shrink in size. So that's basically, in a nutshell, what's going on. Now, the units also talk about the proton-proton chain in detail. And basically what you have two protons, which are the nuclei of hydrogen. So you have two hydrogen atoms, basically, without their electrons, ionized, coming together. As they come together, again, the force of gravity, which plays a very small role in here, but it's the one that is getting them that increases the density. So without the force of gravity, this would not happen. But those are two positively charged ions. So they will repel each other according to the force of Coulomb, electrostatic force. So two positive charges repel. But because of a tremendous heat inside, they have high kinetic energy. They're moving super fast. Once in a while, they will come very close from each other to a point that the nuclear force wins at that point. It pulls them together. So the two protons come together. So this is a rare event, but if it were not for it, there would be no reactions inside the core of the sun. But it is rare enough so that the sun can live for about 10 billion years. If it was any more frequent, the sun would have run out of fuel a long time ago. If it was any slower, the sun would not have enough energy really to shine, okay? So that's basically the bottom line in here. Now, once you have two protons, they're very close from each other at the distance of about a femtometer, which is 10 to the negative 15 meters. At that point, the two nucleons, in this case, proton-proton, they will fuse due to the nuclear force. The strong nuclear force overcomes the force of Coulomb and bring them together. At that point, we have a problem. We have two protons sitting next to one another. This is something that is not good. Nuclear physics requires that one of them has to flip and become a neutron due to another force that is involved, and that is the weak force. So the weak force, one of the protons will radiate immediately a positron, which is a positive electron, and neutrino. Neutrino, which is a particle that doesn't have a charge, extremely light, a lot lighter than an electron, and does not have anything else other than the fact that it's a very, very small particle in a sense. It has a spin, it has other properties. But that's a particle that comes out of this process. So you have a neutron changing into a proton changing into a neutron, giving off a positron, which is a positive electron, and also a neutrino. Well, the positron is immediately canceled. It's going to find a sea of electrons. Remember, we started with hydrogen that is ionized, meaning we have two protons. But what that word ionized means is you have floating electrons every which way in the core. So the positron, the positive electron, immediately after it forms, it encounters an electron, a normal electron, and they will cancel each other. They will annihilate each other, generating energy. So we now have a lot of sources of energy. You have this annihilation of electron-positron that gives off gamma rays, which are extremely high energetic radiations. And then actually the fusion itself produces also gamma rays. So that is where the source of the energy of the sun is coming from, at least at this point. So at this point, we lost our positron to its interaction with the electron. But we also, the net outcome, now I have a heavy hydrogen because this proton neutron that are fused are actually version of hydrogen, an isotope of hydrogen that is a little bit heavier than the hydrogen, called deuterium. So we have a deuterium, and we also have a neutrino plus an abundant amount of energy. Well, the deuterium in this case will capture another proton because protons are available every which way. And remember, we are in an ionized environment where all of the hydrogen basically lost its electrons. And then at this point, you will have two protons after they fuse, again, for the same conditions. Remember, positive charges repel, but then when they have very high enough velocity, they will actually attract each other. So at this point, again, they will attract, and the attraction in this case is going to stick. So in other words, you'll have two protons and one neutron. So this is a version of helium. Actually, this is helium-3 called, because you have two protons, that is helium, the nucleus of helium. But then you have a neutron that formed from that previous step. So now you have helium-3. Plus, of course, energy too, because you're fusing lighter elements toward higher and higher elements. Imagine this process produced helium-3. There is a parallel process also in the same fashion that produces helium-3, where you have initially, as I was saying, in this on this side, you have three protons coming together, giving you a bunch of energy plus a neutrino. On the other side, you also have a similar process that produces a bunch of energy and a neutrino and helium-3. So these are processes that are happening every which way now. Because yes, they are very rare, but there are a lot of them, okay? Because the density is high. So at that point, the two helium-3 nuclei, they fuse for the same reasons that everything has fused, because of the force of nuclear force. Once they fuse, you have now an excess of protons, because you have two protons on one side and one neutron, and two protons on the other side and one neutron. You have two of those protons and the two neutrons that are attached to them, they fuse together to form your normal helium nuclei, helium nucleus. plus they release those 2 protons. So at the end of the day, when you tally everything, you have 6 protons coming together, 3 from each side. And at the end of the day, you have helium atom, that is a helium nucleus that is formed, plus an extra 2 protons that are extracted from the process. So you have 6 protons minus 2 at the end that are coming out. So you actually have only 4 that come in, forming a helium nucleus, plus neutrino from each side. Well, to test this theory, we detected the neutrinos on Earth, and now we know for sure that this is actually true, and we detected the right amount, okay, of neutrinos. So again, you need to read the units, go in detail about them, and try to understand everything. And if you have any questions, please let me know. One item that is important in here also is that those gamma rays are extremely high energy, but the light of the sun is actually not that high energy. So it's actually in the visible range, and actually spans a spectrum that is also in the infrared and actually in the ultraviolet too. And the reason is because you have scattering of those gamma rays within the core of the sun, and that takes a long time. Those scatterings, those collisions, basically with those ions before that ray comes out. And every scattering, its wavelength lengthens a little bit and loses some of the energy until at the end it comes out in the visible range. So this is basically the model that we have for the sun. One of its also important things that you need to explore are the sunspots. And the sunspots basically are formations in the sun due to the magnetic field. The magnetic field has a north pole and a south pole. So what it does in this case, it traps those ionized particles on the surface of the sun and traps them on those field lines. Now, imagine you have a bunch of particles that are pressed against the surface of the sun from one side and a bunch of particles pressed against the other one because they come with different signs. So on the North Pole and the South Pole, as they are pressing, they're pushing against the gas that is trying to rise due to the convection that is underneath that there. So that will basically push on it, and in a sense, lower the temperature of that region of the sun, and they appear darker. So those are the dark spots of the sunspots as we know them. And the frequency of these sunspots is actually related somehow to the atmospheric conditions on Earth. And that is something that you need to explore. How is that frequency? It has to do with the fact that the sun is mainly a gas that is spinning extremely fast. And the equator of the sun, the middle of the sun, spins, of course, faster than slower than the poles. So in this case, this field lines, the magnetic field lines of the sun, some of them will move faster than others, and at some point they start to twist and turn. And as they do, they form these regions of magnetic fields. Those magnetic field lines, at some point, they snap. And in doing so, they reject a lot of materials in every which direction, which are mainly ionized protons and charged particles, electrons. So those are part of the CMEs, the coronal mass ejections, that could cause a lot of problems on Earth. And we have actually part of the things that we monitor are those things on Earth, because they could have devastating effects on technology and electronics. Again, I hope that you guys can go and read all of these units in detail. First of all, because you're going to be tested on these things. And second, also because it's going to lead the foundation for other materials down the road. Thank you.